Welcome back, everybody. We're going to be talking about rotary to linear motion today. So, grab my, here we go. Hey, everybody. So linear systems are very common in our world. Most linear motion systems transform rotary motion to linear motion via screw, although obviously the most simple, a conveyor belt, is a belt drive system. There are two broad categories of screw that are used to do this. There are lead screws, they cost less, they are kind of self-locking and high friction, but they're quiet. And then there are ball screws, and they use kind of a ball bearing structure that's in a helix rather than just in a circular pattern. And they require braking systems. They're much more efficient, and they're way lower friction because the contact is ball bearing contact, so it's a lot lower surface area contact in them. So we'll start off by talking about lead screws. This is the Acme lead screw. So the Acme lead screw is a trapezoidal thread. So you'll notice that it has a flat instead of having a sharp thread architecture there. And you'll see that it has a lead nut, is what that nut is called. And it allows for motion in one direction or another. The trapezoidal geometry there is so that you reduce a little bit of the backlash. If there's a lot of backlash in a normally threaded screw. So you can have various different starts and probably just to review, the number of starts is how many actual threads there are in it. And we'll kind of see that a little later. Lead screws are great because they're cheaper than ball screws. And they're self-locking. They don't need a braking system to them because, and that's kind of an advantage, but it's also a disadvantage because the self-locking happens because they're high friction. And they are quiet. And they provide a wide variety of diameters, from 6 millimeters up to several inches in diameter. But they have some backlash even with all that high friction, and they wear faster than other systems. So that leads us to using ball screws for a lot of systems. And a lot of times you'll see ball screws on CNC machines and other precision linear drives. Ball screws essentially create a helical river of ball bearings that rotate around essentially a C-shaped channel on that forms the threads themselves. They're really low friction and they're really precise, and they reduce a lot of that backlash, which is that part of it where you're going in one direction, and when you change directions, it's transferring the load from the front of the thread to the back of the thread. So that distance that you've got, and it's a necessary thing that you have a little bit of gap there, can be a lot less in ball screws. And as a result, the backlash is a lot less. The advantages of ball screws, they're high efficiency. A lot less torque is being eaten up by friction, so you can have a smaller motor. They're high accuracy because they're extremely precision and they don't have a lot of backlash to them. They're low friction, so they run way cooler. And you have a large variety of diameters to choose from. The big disadvantage is cost because you've got a lot more moving parts and a lot more precision parts. So let's talk about lead and pitch. Lead refers to the linear distance traveled for a complete turn of the screw. So the lead is how far it goes for one rotation. Pitch is the distance between the screw threads, right? And these two terms are often used interchangeably, but and the thing is, for single strut screws, the lead and the pitch are equivalent, right? It's for one rotation in a single start screw, it's going to be the same as the lead is going to be the same as the pitch. But once we start dealing with multiple starts, where there's more than one entry and more than one pattern in our thread helix, and this down here on the bottom right here, actually let me move my head over to the other side. I'm going to move my camera over here. Quick little thing there so that you can all see that. So essentially, with a double start, there are two areas at the base of the screw that the threads can be engaged from. And that means that those individual threads are alternating. You can see the colors there. So one thread to the next thread is going to be longer. It's going to be double the pitch. So the lead and the pitch are the same on a single start, but now they're double. In a 4-start, they're quadruple, as you can see there on the bottom right. So the only reason why you use 4 starts or double starts for these things is when you need the motion to happen very fast, because they're actually pretty poor at transferring torque, which makes sense. You don't get something for nothing, and that's kind of the whole thing with mechanical advantage. So this should just be a little bit of review. You covered this in IMO, but wanted to get this to you here. And advance to the next slide. Now, the screws are not the only way in which we can transfer linear power. Another way that we can transfer linear power is rack and pinion. You may be familiar with rack and pinion steering on a car. This is what a rack and pinion looks like. It's a gear that's round, called a pinion, traveling along a toothed linear way that's a rack. So that might be straight teeth, or it might be angled teeth like you see on the bottom right. Now, the linear system is built around not just having the lead screw. You also have to have the guides associated with that. And so these are examples of linear systems, and quite often you've got essentially 2 bearing surfaces in addition to the lead screw to make up your system, so that it's basically guided along there, and so you'll have linear bearings, 2 sets of linear bearings for each guided lead screw on these. So you can see a number of these different variations on that effect. You can also have belts and pulleys act as linear drives, and you'll see this on the 3D printers that we have in the back. So it might be worth taking a look at that again. You've already kind of examined it in the past. So belt drives, they consist of synchronous belts and pulley systems. It would not make any sense for you to use something that would slip, because you want to have precision motion in a linear system like that. So you'd often drive that with stepper motors. So you'll see this in index material conveyance, 3D printers, wherever you need lightweight, because belts are way lighter weight than the big rods and lead screws are. So it's very helpful for keeping things light, and that's why you'll see them on the gantries of 3D printers. They're inexpensive compared to other systems. They have fewer moving parts. They have high speeds, very high speeds. Belt linear drives are what are used in most at-home printers, for instance. So they're very inexpensive, and they can do really high speeds. That's why you can see the head of your printer go back and forth, your inkjet printer go back and forth really, really fast. The disadvantage is obviously they can only handle lighter loads, because they're just kind of not quite as beefy as the other options. And belt tensioning is critical for reliability and repeatability. So here's a rack and pinion drive. And rack and pinion is used where it requires high loads or where space is at a premium. Rack and pinion can be tucked away down the sides here like you see on this machine here. And that makes it very useful. And it can be used on gantry systems of all sizes, from the very small to the very large. Rack and pinion can be used on drives that are essentially riding on train rails. The advantages and disadvantages of rack and pinion: you've got high precision, high speed, high load capacity, and compact design. But the cons are you've got limited travel. You've got a lot of wasted space on either end. You've got high cost, like way higher cost than belts and pulleys. And you've also got lubrication requirements. They also can be a little noisy. And alignment is key with rack and pinion, whereas belts are a lot more forgiving. So you'll see these used in very large CNC equipment, gantry systems that are like where you have a very large bed, such as plasma cutters, lasers, routers, cranes, heavy industrial processing and conveyance when the loads are extremely large. And then you have things like this, which are our ball screw linear drives. And these systems often have either a stepper or a servo motor as the input. They're used on CNC equipment of all kinds due to their precision and reliability. Packing and sorting machines, all kinds of various different high precision linear motions are often best handled by ball screw linear drives. They are very high precision, like the ball screws that are in them. They don't move around a lot. They're very tight in tolerances. They can be constantly run. They can be relatively high speed and high reliability if you've set them up properly, and very efficient at the same time. The cons are these systems are a little bit bulky when compared to rack and pinion. Ball screws are expensive. They're sensitive. They, like if we get dust, powders, anything in there, so they have to kind of be guarded behind several different layers in order to make sure that we keep those contaminants out. They're also expensive. Like the biggest thing is they're expensive. And then once you get one axis, it's really easy to add multiple axes. And I think that's really just something for you to leave this video kind of thinking about. You can add different axes, essentially your CNC machine, your 3D printer, most of those are 3-axis systems, but then you can have more axes off the top of that. And you don't have to keep to one style system for an axis. Sometimes you'll have a Z-axis that is a lead screw, whereas the X and Y are ball screws, or any combination thereof. You might have the X and Y be rack and pinion, and the Z-axis be a ball screw. So you can have any number of permutations of recombining these same ingredients to get different geometries of machine envelopes. So that's all I've got for you on linear drives. We'll see you in the next video.